Libraries have to be created somehow. Fortunately, it's a rather simple process. For static libraries, you want to compile your code into object code. Remember the -c flag. It indicates to just compile the file without linking it and turning it into an executable, which resulted in it becoming an object code file. Next, we want to archive the object code with AR, an archival utility. I know the arguments are rather obtuse. R means to insert files with the replacement in case the archive already exists. C means to create the archive, and S means to write an object file index into the archive, whatever that means. I personally wouldn't worry too much about these exact options. I personally just remember AR, RCS. Dynamic libraries are a bit different. Again, you want to compile your object code, but now with the -fpic flag, which specifies it to compile it as position-independent code. The implications for this are better left for classes that discuss operating systems like EECS-482 or computer architecture like EECS-470. Once you have them, you can link your objects into a library file with the -shared linker flag with LD, the linker, or your compiler, like GCC. The -shared linker flag specifies to create a shared object, in essence, a dynamic or shared library. It can get deeper. Here's some notes about them on the Linux documentation project. This document discusses things like versioning and maintaining binary compatibility. If you want to go even deeper, you can take a look at Ulrich Drepper's Guide on Writing Shared Libraries. It's a really great read and was something that was recommended to me by my interviewer during an internship interview, which I later got an offer from, by the way. Let's create a really simple toy library. Let's say it contains a function that adds 2 numbers and then returns them, and then create 2 executables that use it, just to illustrate the idea of sharing a single object. Alright, cool. So I'm going to go ahead and make my library file. Let's call it libadd or something like that, or just call it add.c. And inside this file, it's going to have, let's say, add, a function called add that adds 2 integers. So int a, int b, and then all it does is return a plus b. Simple and easy as that. And I'll have an add.h. And inside this will declare my function, my int add int a int b. Now let's say this is going to be in libsource. Move add.c to libsource. Move add.h to libsource. Now let's say I have a directory called source over here. This is going to be just say these are my regular programs. And let's say I write 2 programs. I call this app1.c, and this is just C or regular C boilerplate, and main int argc chars argv turn 0. And I'll go ahead and copy the app1 to app2 just so I don't have to write the boilerplate again. And let's say we have this library and it's inside of our, search path. We can do #include add.h. So there's actually a difference between the angle brackets and double quotes when it comes to including things. So with the angle brackets, it's actually going to look through what's known as like the include search path or the header search path, which is basically a set of directories where it's going to look for these header files that you name out here. Chances are, because this library isn't installed system-wide, it won't be able to find it, so we're going to have to deal with that when we actually compile our code to add another place to look for header files. Oh yeah, and if it doesn't find them in the system-wide locations, it's going to look relative to the location of the file. Hash include with 2 double quotes will actually look relative first to the file, and then afterwards it'll look through the search path. So if you didn't know the difference there. Yeah, I'll have add.h, I'll do x is equal to 5, y is equal to 10, and printf app1, or %. I'll put the name of the executable here, and then %d plus %y, or %d is equal to %d as my format string. So I'll say argv0, the name of the executable, x, y, and then add x and y. So no, I didn't have to do the function declaration myself. That's already handled by the hash include of add.h. And over here in app2.c, I can do the same thing, hash include add.h, and then do something very similar. Maybe I can say for int I is equal to 0, I is less than 5, plus plus I. And I'll say yeah, 5, yeah. I'll say x is equal to I, y is equal to I plus 1, and then printf %d plus %d is equal to %d, x, y, and then add x, y. And these are just two different programs that do different things. And this is going to fail, but if I try to compile these, app1.c, you'll see that, for one, it doesn't know where add.h is. So our simple remedy for that is -i. Let's say the lib source directory is where the header include directory is, and you can see that it was able to find it. Now it just errors because I made a dumb mistake in these files, such as not declaring what types these are, because I'm used to Python now. In x and y. So now compiling it again, you see that it doesn't know what the add function is. Well, let's go ahead and rectify that. Let's actually create our library functions, or libraries. So what we can do is say, I'll create a dynamic version and a static version just for completion's sake. So I'll say make dir lib. I'll say lib is this location where I'm going to create my directories or plot my libraries down in. And I'll say make dir obj, a place to put my object code files in. So I can say gcc-c for compile it as a object code file. Plop it down in here. I'll call you add.o. And you know what? To kind of separate them, I'll also make a static and make a dynamic separation there. So I could say, all right, gcc-c-o inside of obj. This is going to be the static version. I'll call this add.o. And what I'm going to compile is libsource/add.c. Cool. We are able to compile it. And to compile actually, I'll go ahead and finish the static version. And to create the actual static library, I'll do arrcs, supply the place where it's going to go, lib, and this is going to be lib add.a. And then supply my static, the object code file meant for a static library. So if we look inside of lib, we can see that we have libadd.a now. And now let's do the dynamic version. We can do gcc-c-fpic, obj, dynamic, add.o. So we're making a dynamic version of our object code. Libsource and add.c. We've created it, compiled it, no errors. And then I can do gcc shared -out lib add.so, and then supply my object code file there, add.o. This will generate the SO version, the dynamic version of it. I could also just directly invoke the linker as well if I wanted to. If I deleted lib add.so, I could also explicitly say link it with the linker. which under the hood, when I run GCC, it's going to also run the linker anyway. Yeah, so from the perspective of out here, let's go ahead and compile our, well, I'll put programs now. I could say, all right, GCC -o app1. I'll say this is going to be the static version. Or rather, let's say this is going to be the, yeah, let's go with this being the static version for now. So if I do source slash app1.c, then afterwards, now I have to, well, I have to supply additional information such as where the header files are. So that would be -I and say, all right, they're inside of lib source. So now we can resolve the hash include add.h. And then now I'll supply some linker flag. I could say -L to say, all right, link against a particular library in this particular directory. Or rather, supply a particular directory as a place to look for library files. Because if I just do L add here, it doesn't know where the add library is. But if I do -L and supply lib, it suddenly knows, okay, look inside my current directory, inside the lib directory there. You see that we get a success in our compilation. And I could do the same thing for, yeah, and when note that because I did this, and there's both a static and dynamic version, if I LDD on my app1 static, you see that it looks for a lib add as a dependency. So what I have to do is lib, or L:, lib add dot A to specify, I actually want the static version here. If I do LDD on app1 static, you can see that lib add is no longer in the list. And we can do the same thing for app2 as well. And now let's try to link against ours in the dynamic form. I'll say app2 dynamic, same thing. It's even easier. We accidentally created the dynamic version one earlier than app1. So just -L and then add, and it automatically goes for the dynamic version instead of the static version. Now we have all we have all of them here. We have app1 dynamic. Ooh, but when you try to run it, there's another issue here. It goes and tries to find the libraries that it's using. And that's because, well, the add library isn't installed system-wide. It's just sitting in this random lib directory here. So there's a few things that, like when you actually install a library, it'll end up being installed system-wide so the linkers and loaders can find it. But whenever you're like doing some development on your own library, you might take advantage of the LD library path variable, which is very similar to your regular path variable, except this is specifying directories to look for libraries. So I could say, all right, look inside of lib. And then for this, the way I structured my command here, I'm specifying that set this environment variable for this particular command that I'm running. You see that we can successfully run it. Ooh, looks like I compiled app1 dynamic with app2.c. Yeah, app1 dynamic, and then app2 dynamic. And then if we want, we can just run the static ones just normally because the library is already put inside of the executable. Yeah. And if we want to look at the sizes of these, because the library is so small, we're not actually seeing that big of a size. If I take off the, if I look at app1 static here, stat app1 static, see that this is 20,000 or 20,608 bytes. If I do app1 dynamic, you can see that it is very slightly smaller because this is an absolutely tiny function. But to note, it is slightly smaller. And also, you also got to see the lack of drama when linking against a static versus a dynamic library here, because with the previous example with libm, it was a bit weird because of how libm is designed around and how it relates to the C library. But here, with our own little custom libraries, we can see that we can easily switch between the dynamic and static version just by tweaking our -l command. Hopefully this was a nice taste of how to use libraries and create them as well. There's a little bonus there.